Howdy. In this video, I will demonstrate my lab3 project on CUDA programming and custom Python library creation. The goal of this lab is to compare matrix multiplication performance across four implementations: CPU baseline, naive CUDA, optimize CUDA with shared memory tiling, and the Kubelos library. I also implemented an image convolution and create a Python callable shared lab. I'm running this on Windows with the NVIDIA RTX 4080 GPU and CUDA Toolkit version 13.1. So now let me verify my development environment. So as you can see, I have CUDA 13.1 installed. And my RTX 4080 is detected with appropriate driver version. Now let's move to part 1. Part 1 of the lab requires implementing matrix multiplication on the CPU. Here is my C implementation. It uses a standard triple nested loop algorithm. The outer two loops iterative over each output element position I and j, and the innermost loop computes the dot product of row I from matrix A and column J from matrix B. Now let me run it with different matrix sizes. So for n equals 512, it takes about 0.6 seconds. And for n equals 1024, it jumps to over 10 seconds. As you can see, the CPU execution time increases dramatically as the matrix size grows. This establishes our baseline for comparison. Now let's to part 2, the naive CUDA implementation. In this kernel, each thread computes one element of the output matrix. So the thread calculates its global row and column position using block IDX, block dim, and thread IDX. Then it performs the same dot product computation as the CPU version. The key difference is that instead of computing elements sequentially, we launch thousands of threads in parallel. Now let me run this with the same matrix size. So you can see where n equals to 512. So it takes only 0.13 milliseconds. And for n equals 1024, it takes about 1.1 milliseconds. And for n equals to 2048, so it takes about 8 milliseconds. So the requirements are impressive. So for example, for n equals 1024, the naive GPU takes only 1 millisecond compared to 10 seconds on the GPU. So that's about 10,000 times faster. So however, this naive implementation has a memory bottleneck. Every thread reads from slow global memory for each multiplication operations. R4 focuses on optimization using shared memory tiling. The key insight is that shared memory is much faster than global memory. In my optimized kernel, I divide the matrices into 16 by 16 tiles. These are the shared memory areas, DSA and DSB. Threads in each block collaboratively load a tile from global memory into shared memory. Then all threads compute using this cache data before loading the next tile. Notice that the sync thread calls. These synchronization barriers ensure all threads have finished loading before we start computing, and finish computing before we load the next tile. So now let me compare the performance. So for n equals 1024, it takes about 0.8 milliseconds. And for n equals 2048, it takes about 6.3 milliseconds. And for n equals 4096, it takes about 61 milliseconds. So compared to a naive version, the tiled implementation is much faster. So the benefit increases with larger matrices because we are reducing global memory bandwidth consumption by reusing each data element 16 times. So now let's move to part 6. Part 6 uses NVIDIA Kubelos library as a performance reference. So Kubelos is highly optimized by NVIDIA engineers and can leverage tensor cores on modern GPU. So one important detail is Kubelos uses column major storage like Fortran while C uses row major order. To handle this, I pass matrices B and A in that order. You can see DB comes before DA. Now let's try and test their performance. So you can see for n equals 1024, it takes about 0.1 milliseconds. And for n equals 2048, it takes about 0.8 milliseconds. And for n equals to 4096, it takes about 5.6 milliseconds. So the result shows Kubelos is significantly faster. You can see at n equals 4096, it runs in just 5.5 milliseconds, which is nearly so it's more than 10 times faster than my optimized tiled kernel, so which is 61 milliseconds. So this demonstrates why production applications should use vendor-optimized libraries for standard linear algebra operations. Now let me summarize the performance comparison across all implementations. This chart shows execution time for different matrix size. Looking at the color, CPU is showing red, always the slowest. Naive CUDA is shown in blue. Optimized CUDA is showing orange, and Kubelos is shown in green. Interestingly, at a small size, like n equals 128, Kubelos is actually slower than my naive and optimized implementations. This is because Kubelos has initialization overhead that dominates for small matrices. But as matrix size increases, Kubelos becomes the fastest. So the GPU provides massive speed up compared to CPU, especially for large matrices. So now let's move to part 7. Part 7 requires creating a shared library callable from Python. I compile my optimized CUDA kernel into a DLL file. The key parts are external C prevents C++ naming mangling so Python can find the function, and the export declaration makes the function visible when loading the DLL. And the wrapper function handles all GPU memory management, allocating device memory, copying data to the GPU, running the kernel, copying results back, and freeing resources. So, and and in Python, I use C types to load the DLL and define the function signatures. NumPy arrays are converted to C pointers. Now let me run the test script. So as you can see, for small matrices like 512, the GPU is actually slower because of the PCIe transport overhead. Sending data to and from the GPU takes more time than actual computation. And for n equals 1024, GPU and CPU are about even. But for larger matrices like n equals 2048, the GPU computation becomes the dominant factor, achieving 1.58 times speedup over NumPy. This demonstrates why GPU acceleration is most effective for large workloads, while the computation time outweighs the data transfer cost. The second part of the lab involves implementing image convolution. For the CPU version, I use a four-layer nested loop structure. Outer loops iterate over image pixels. Inner loop applies the filter kernel. For the GPU version, I map one thread per output pixel. The key optimization here is storing the filter kernel in constant memory. Constant memory provides very fast cache access because all threads read the same filter values. This is called a broadcast. And the kernel applies the filter with boundary tracking for zero padding. Now let me run both versions and compare. So you can see the CPU takes about 0.1, 0.2 seconds for a 1024 by 1024 image with a 5 by 5 for a 1024 by 1024 image with a 5 by 5 filter. And you can see the GPU only takes about 0.04 milliseconds. So that's a lot of speed up. And I also create a Python script that applies various filter to a test image using my CUDA library. Here you can see the result. The original image contains geometric shape, a cycle, a square, and lines. I also create a Python script that applies various filters to a test image using my CUDA library. Here you can see the result. The original image contains geometric shapes, a circle, square, and lines. The Sobel X filter detects vertical edges. The Sobel Y filter detects horizontal edges. The box blur smooths the image, and the sharpen filter enhances edges, and the edge detect filter using Laplacian identifies all boundaries. So in conclusion, this lab demonstrated the massive performance benefits of GPU acceleration for parallel workloads like matrix multiplication and image convolution.